Okay, we were about to consider and to investigate the properties of the linear adiabatic wave equations, adiabatic wave equation. One point we have found was that the linear adiabatic wave equation is a Sturm-Liouville type equation, and we can take all, we can adapt all the properties of the Sturm-Liouville problem and make use of it for the adiabatic wave equation. Well, one of the most important properties is that the operator, the differential operator, is self-adjoint, and therefore the frequencies sigma squared, not the frequencies themselves, but the frequency sigma squared have to be real, and we have explicitly proven it by considering the properties of the differential operator. There is another property which I would like to comment on in detail. This is once we consider two functions zeta m and zeta l, which are supposed to be eigenfunctions for two different eigenvalues, sigma m squared and sigma l squared, then we have, according to the perturbation equation, that sigma m squared times the function g acting on the function, the eigenfunction zeta m, is differential operator acting on zeta m minus h times zeta m, and we consider the second eigenfunctions zeta l or sigma l squared. So we have the equation for sigma l squared times g acting on sigma zeta l is equal to the differential operator acting on zeta l minus h acting on zeta l. For convenience, we take the complex conjugate of the second equation. Complex conjugate means all these quantities are real, so only the complex conjugate of the eigenfunction is to be applied here. Operator d is real and h is also real. What we do now is we integrate the first equation with the second eigenfunction, zeta l star, and integrate the second equation with the first eigenfunction, zeta m, and integrate over the integration interval. Then we are left with zeta m squared times the integral over g times the product zeta l star times zeta m, and down in the second equation we have zeta l star times zeta m. Then we have the term containing the differential operator zeta l star times d zeta m, and in the second zeta m times d zeta l star minus h times zeta l, where is it? L star is the product here times zeta m, and of course down the second one is zeta m times zeta l star. Okay, now we know that these two terms are the same because the operator d is symmetric, so we can interchange zeta l star and zeta m, and we can subtract these two equations. Okay, then these two terms will cancel because the operator is symmetric, and these two terms will cancel because of obviously zeta l star is equal to zeta times zeta m is equal to zeta m times zeta l star. So the difference of the right hand side is 0. Main argument is that the operator, the differential operator, is symmetric. Okay, what are we left with? We are left with then of course, this product zeta l star times zeta m and zeta m times zeta l star is the same. So these two integrals are identical, and we have sigma m squared minus sigma l squared times the integral over the function g times zeta l star times zeta m has to be 0. What does it mean? Well, if m is not equal to L, then this bracket is non-zero, then obviously this integral has to vanish. That means the integral over G times zeta L star times zeta M is 0 once we do not have the same eigenfrequency sigma M. Sigma M is not equal to sigma L. If M is equal to L, of course, then we have that. Then we have the following integral. Then we have G integral over G times zeta M star times zeta M, which is the modulus of zeta M squared, zeta M squared. Of course, this quantity is real, and this condition or this reality may be used for the normalization of our eigenfunctions, normalization such that this integral is unity. This means normalization. Okay, so we can normalize our eigenfunctions in a way that the integral over the function g times the modulus of the eigenfunction squared is unity. What does this mean? Well, this means normalization of the eigenfunction, and this condition, if we have two different eigenfrequencies and we consider the integral over the product of two eigenfunctions which do not belong to the same eigenvalue. What does it mean? If you remember possibly quantum mechanics, in quantum mechanics you have similar problems. How do you call it? The eigenfunctions are orthogonal. So their product or the integral over their product is 0. So the eigenfunctions of our linear adiabatic wave equations, they form an orthogonal system, and if you normalize it, then you have a so-called orthonormal system. This means you can expand any function depending on radius in terms of these eigenfunctions of the adiabatic wave equation. Well, you haven't proved, or we haven't proven, and this is a little bit more difficult, that it's a complete orthogonal system or orthonormal system, which means that any function can be represented as an infinite sum over the eigenfunctions of the problem. This might be this property is sometimes used if we go to astro and helioseismology. Then you can expand your functions you want to represent in terms of the eigenfunctions of the adiabatic stability problem, either on the radial or the non-radial problem. So this is an important problem, or important property, which might be used later on in helio and astroseismology. They form the eigenfunctions, form an orthonormal system. Here explicitly shown for the case of radial adiabatic perturbations. Okay. Well, now I would like to comment on some additional properties of the linear adiabatic wave equation for radial perturbations, but without proof, I will resort now to the standard results known from the mathematical studies of Sturm-Liouville systems. So there are many theorems about Sturm-Liouville systems. To remind you again, Sturm-Liouville systems are typically of the form or are defined by an equation, a differential equation of this form, and we have seen that our problem is exactly of this form with the property that f and g are positive functions. So the results, we can take the results which are known from the mathematics of this system and apply it to our linear radial wave equation. Okay, so what are the main results? There are many results, but I will refer only to those which are interesting to us. Okay, the first theorem states there are infinitely many real non-degenerate eigenvalues lambda. Lambda is now the equivalent of sigma squared, with a smallest eigenvalue lambda 0 and an infinite limit. So the accumulation point of the eigenvalues lambda of such a system is infinity, and there's a lower bound to the eigenvalues, and there is the smallest eigenvalue lambda 0. Moreover, the eigenvalues can be put in a countable sequence, so you can arrange them according to their order. The lowest eigenfrequency is, or lowest eigenvalue is lambda 0. Next higher lambda 1, smaller than lambda 2, smaller than lambda 3, and so on up to infinity. So this is a well-ordered scheme of eigenvalues. This is important because in general, the eigenfrequencies and the eigenvalues we consider in our systems are not by any means not well ordered. They are completely confusing. So there is no ordering scheme for the eigenvalue except for the linear radial wave adiabatic. So that's all the linear, radial, and adiabatic. Then you have an ordering scheme and a well-ordered scheme of eigenvalues. Okay, this is a very important property. And the second property, which is also remarkable, that the eigenfunction, well, it's formulated a bit misleading. The eigenfunction is, of course, not lambda n, but it's the eigenfunction which belongs to the eigenvalue lambda n, has exactly n zeros in the integration interval. So this is not true for any other problem, but for this problem, we have the property that if we look for the eigenfunction of lambda 2, then we will find 2 zeros of this eigenfunction in the integration interval. So if you see the eigenfunction, then you know the order of the eigenvalue. The opposite is not true. If you see the eigenvalue, you don't know which order it has. But if you see the eigenfunctions which belongs to that eigen frequency or eigenvalue, then you know its order, you know which is the number, the index n of this eigenvalue and eigenfunction. So you can immediately read off from the eigenfunction. Okay. Well, the third point is you can also show, I haven't shown it here, that the orthonormal system is complete. This is an important additional property. So it's a complete orthonormal system. They are not only orthonormal and you can expand some function, but you can expand any function. This means completeness. Okay, so this is the third property. So we have in the case of radial linear adiabatic perturbation problem, we have an ordering scheme for eigenvalues and eigenfunction. Lambda 0 and y0 is the so-called fundamental mode. Lambda n and epsilon yn is the nth overtone. And this and the number of zeros of yn indicates the order of the eigenvalue and eigenfunction n. Okay, keep in mind this ordering scheme is valid only for radial adiabatic perturbations. Any other adiabatic non-radial doesn't exist. Non-adiabatic there is no existence in non-adiabatic and in any other system. Despite this fact, people classify modes according to that scheme. Sometimes the scheme of eigenvalues you see remind us of this scheme having a lowest order, first overtone, and so on. But mathematically speaking, this ordering scheme is not present once you deal with another system rather than this radial adiabatic system. It's just reminds you of this ordering scheme And if you look for the zeros of the eigenfunctions, sometimes it fits, but there are cases where it doesn't fit at all. And if, for instance, modes cross each other, then the ordering system is gone anyway. So keep in mind, even if people address some mode as a P1, P2, P3, or G1, G2, G3, the ordering scheme is not present in the general case. It's only found here. And it's simply that people take this ordering scheme and adopt it for the general case as well. So be careful if in the fully non-adiabatic case someone speaks about the first overturn or the fundamental mode. You have to be very, very critical. This is not necessarily true. So the ordering scheme is only present for a Sturm-Liouville problem. Okay, questions? Okay, now we turn to some other property related or which can be proven for self-adjoint and nicely behaved Sturm-Liouville problems, which is the fact that we can deduce our perturbation problem from a variational principle. And the variational principle itself has the advantage that we can derive some integral criteria from the functional formulation of the perturbation problem. Okay, how do we get a functional a variational principle for the eigenvalues, and how can we derive the perturbation from a variational principle? I heard that some of you might be familiar with variational calculus. This is usually done in theoretical mechanics, in classical or analytical mechanics, or in quantum mechanics too. So, but if you don't understand any detail, it will not be critical here. Okay, so what we do to obtain a functional from whose variation we can derive, or which is equivalent then to the perturbation equation, we simply multiply the wave equation with the complex conjugate of zeta and integrate over the volume or over the integration interval. This is the differential operator of the linear adiabatic wave equation multiplied with zeta star, the complex conjugate of zeta, and these are the remaining terms which go with zeta. So this is the modulus of zeta squared times the remaining functions, which is the sigma squared times the function g and the function h. Okay. Now same procedure as in any step. We do partial integration of our differential operator here, and we put this derivative to the zeta star by partial integration. Then we have a boundary term, zeta star times gamma adiabatic p times r to the fourth times d zeta by the r between 0 and between the center and the surface of the star. Again, these boundary terms are 0 because p naught is 0 at the outer boundary and r to the fourth is 0 at the inner boundary. Well, minus then the derivative of zeta star times the remaining quantity here. So this is nothing but d zeta by the modulus of d zeta by the r squared, modulus of d zeta by the r squared, which is left here. So this is a nice positive and real quantity which is left, which we achieved simply by partial integration. The rest, of course, is real anyway. Okay, so we can now solve the resulting equation. This equation here we can solve for sigma squared. That's what we do. Okay, so sigma squared times we also take along with sigma squared the dynamical time scale, which is the root of G times the mean density. So this is then a physical quantity, a physical time, because sigma squared was the dimensionless time, and we get, for sigma squared, we get a ratio of 3 integrals. So this is the integral which stands at sigma squared is the zeta modulus of zeta squared times rho times r to the fourth. This goes into the denominator, and these integrals associated with h and the differential operator, they are in the nominator. So we are left with the following expression. This is essentially the function g, which apart from this factor, so we denote it with g tilde here. This is given by density times r to the fourth times the modulus of zeta squared. This is the remaining of the differential operator, and this is the function h times the modulus of the displacement squared. Well, the right-hand side is a so-called functional depending on a function zeta. So sigma squared may be expressed as a functional capital F, which depends, the integrals depend apart, of course, from the stellar model, which enters here through P naught, rho naught, and gamma adiabatic. The right-hand side depends on the function zeta. And now we apply this so-called functional, we apply the variational calculus to this functional zeta. Well, that means we vary the functional zeta with respect to a variation of the function of a, so to say, arbitrary function zeta. Okay, so we calculate the variation of the functional with respect to variation of the functions zeta. So delta f, this is the variation of this functional f, is given by the variation of the integrals on the right hand side. So first we have to vary all those places, or we have to apply the variation at all those places where the function zeta is contained. This is, for instance, at the denominator here. We have zeta star times zeta. Well, a variation acts like differentiation. So you have a kind of quotient rule, a kind of product rule, and we apply the product rule with respect to the functional variation of this integral here. So this gives minus 1 over this integral squared times the variation of this, of the integrand. This is g tilde times, well, this is a product, so we apply the product rule. This is delta, the variation of zeta star times zeta, plus zeta star times the variation of zeta. Plus, the next step is then take this and keep this constant and vary the nominator. So it works like a differentiation. So this is plus, keep this part constant and vary these two integrals. So this is the zeta star by the r times d by the r, the variation of zeta, plus the d by the r, and then the next variation will be zeta star will be varied delta zeta star times d zeta by the r. And for this term we have h times delta zeta star, which is the variation of this term, times zeta, the product rule, plus zeta star times the variation of delta zeta. Okay? Now we insert for the quantity for this part divided by one of these integral, we insert the original functional because the original functional is given by this quantity, and of course, well, this quantity is given by sigma squared 4 pi g times the mean density. Go here. So f of zeta is equal to sigma squared, and this quantity is, so to say, sigma squared times 4 pi g times the mean density. And then we can write at least part of it. The denominator divided by one of these integrals is just sigma squared times 4 pi g times the mean density. And we are left then with the following result, delta f. Well, let's see, then we have a common denominator, which is this part, and we have the following result. Then we can, after some algebra, delta f is 1 over this integral in the denominator times, now we separate according to the variation of delta zeta star and delta zeta. Actually, the expressions are pretty much the same. So what is left on the denominator here is two terms involving either delta zeta star or delta zeta, and the factors which have to be multiplied with this are minus sigma squared times 4 pi g mean density. That comes from inserting for parts of the integrals the functional f of zeta itself times g tilde times zeta minus d by dr, actually no, f d zeta by dr minus h z. Let's perhaps look to convince you where this comes from. So the sigma squared term, this gives a sigma squared times the g tilde times both delta zeta and delta zeta star, either multiplied with zeta star or zeta. And here we have those terms which are connected with delta zeta. This gives one term which goes with zeta star, or with delta zeta star, this goes with the corresponding term at d by dr, d zeta by dr. So we collect those terms, or we separate or collect those terms which are proportional to delta zeta star and those terms which go with delta zeta. So we end up with the following result. The integral which remains here is delta zeta star times sigma squared g tilde minus the operator, the original differential operator for the linear adiabatic wave equation, minus h zeta. And what we see here, well, we have the complex conjugate of the delta zeta star here, and in the bracketed term, it's exactly the same expression, but with the complex conjugate of the function zeta star instead of the original function zeta. So what we have here is some function and its complex conjugate. So the second terms are simply the complex conjugates of the first ones. These are the complex conjugate of this. This is complex conjugate of that. This is complex conjugate of that, and this complex conjugate of that. The sum of a quantity, a complex quantity, and its complex conjugate. What do we get from that? What do we get if we have a complex number and we add a complex number and its complex conjugate? You are left with a real part of the, or 2 times, actually, it should be 2 times the real part. So what we are left with, apart from factor 2, sorry, the factor 2 is missing, but it doesn't measure. So this should be equal to 2 times the real part of delta zeta star times delta zeta star times the bracketed terms given here. So minus sigma squared 4 pi g rho bar times g tilde times zeta minus the differential operator of the adiabatic wave equation minus h times zeta. Now, well, the variation is arbitrary. It's just done to have an arbitrary variation of the function delta zeta or delta zeta star equivalently. So what does it mean? What do we derive from that? So if this is arbitrary, then if we require delta f equals 0, or we are looking for the condition which follows from delta f equal to 0, delta zeta star is arbitrary, then this integral has to vanish. That means if delta zeta star is arbitrary, then the bracketed term has to vanish. And the bracketed term to vanish is, well, this is the differential operator of the linear adiabatic wave equation, and this is the term containing the eigenfrequency and the additional term h zeta. So the vanishing of this bracket is simply our linear adiabatic wave equation. It's identical. If we require this bracketed term to vanish, then this is simply the differential form of the linear adiabatic wave equation. So what we see is either we require the vanishing of this term, which is equivalent to having a solution of the linear adiabatic wave equation, and in this case, the variation of our functional vanishes. So the vanishing of the functional is equivalent to the differential equation for linear adiabatic radial perturbations. Okay? Because this variation is arbitrary, so the vanishing of the integral and delta f is equivalent to the vanishing of these bracketed terms. This bracketed terms, vanishing of bracketed terms means this is the linear adiabatic wave equation. So what we found then is the solution of the differential equation for linear radial adiabatic perturbations is equivalent to a local minimum. Delta f equal to 0 means this is a local minimum of the functional with respect to any admissible function zeta. Go back to the f. So delta f equal to 0 means the variation of f vanishes. F was a functional. So this means the minimum of f with respect to the variation of the functions on the right-hand side under the integral. Variation of the functional vanishing means we have, or this is equivalent to having a solution of the differential wave equation. Okay? It doesn't seem to be too familiar to you. This is a typical approach in analytical mechanics and also in quantum mechanics. Okay, so delta f equal to 0, minimum, local minimum of the functional is equivalent to having the adiabatic wave equation, which is the 0 of this bracketed term. Okay, so once we are looking for eigenvalues, we could also go and see what are the local minima of this functional. And if we have a local minimum of this functional with respect to the to admissible functions zeta, then we have an eigenvalue, because we saw the value of f is simply the eigenvalue itself. F of zeta is sigma squared times 4 pi g rho, but only, of course, in that case if we have a solution of the wave equation on the right-hand side if f has a local minimum. So we are looking for minimum of the functional, and if we have a minimum, then its value at the minimum will be the eigenfrequency. So this is another approach, an integral approach to determine the solution of a perturbation problem or to determine the solution of the boundary eigenvalue problem. Okay, so that means solution of the wave equation is equivalent to vanishing variation, here a local minimum of the functional f of theta, and the minima of f of theta correspond to the eigenvalues in the sense that sigma squared times normalization is the minimum or local minimum of f of theta, minimum taken over all admissible functions theta. Okay. How can we use this? Well, it's a lot of mathematics and it's rather counterintuitive going through all these self-adjoint mathematics here, which is hopefully known to you from quantum mechanics. It's exactly the same formalism, and in quantum mechanics you meet or encounter many Sturm-Liouville problems, and therefore this approach should be used, or you can have an exercise for quantum mechanics by going through the analysis here. It's very much the same. Unfortunately, well, it's nice to have it. Therefore, I do it in detail because in general, if we go to non-adiabatic or non-radial problem, the operators do no longer have any properties. So all the operators we are dealing with do not have any properties, but in selected cases, like the radial linear adiabatic case, the operators have a property and have properties, and we can work with these properties. And similar to as in quantum mechanics, the operators are all self-adjoint, have nice properties, and we can use these properties to determine properties of the system, deduce physical consequences from it. This can be done here only for very selected cases, and if we are in a position to do that, then I apologize. I'm doing this here. Okay. But we can deduce a very nice and important property or important criterion from this, from the fact that the eigenfrequencies are minima of this functional. Okay, why not looking for the lowest eigenvalue? Well, the lowest eigenvalue, I remind you of the fact that the sigma squares are well ordered. Sigma 0 squared is smaller than sigma 1 squared, than sigma 2 squared. So, and stability or instability in the adiabatic systems can only become or can only enter through negative values of sigma squared. So once we have an unstable, an radially adiabatic unstable star, how will instability enter the system? Well, if they are well ordered, the instability will in any case be seen by the lowest eigenvalue. If the lowest eigenvalue, if sigma naught squared is smaller than 0, then we have instability. The second, it might be that the second the sigma 1 is also contributes to instability, but if sigma 1 contributes to instability, then sigma 0 will do in any case. So to determine whether a star is adiabatically unstable, we need to consider the lowest eigenvalue and need to determine whether sigma naught squared is smaller 0 or bigger than 0. If it's bigger than 0, then the star is adiabatically stable. But if sigma naught squares falls below 0, then we have an adiabatic instability. Well, now we have a procedure to determine the sigma squared as the minimum of the functional. So this might help to determine or give you an upper bound or lower bound for the value of the lowest eigenvalue, because then we have to look or we have to search for the absolute minimum of this quantity on the right hand side, because it's a relative minimum for any of these eigenvalues, and of course it's the absolute minimum if we are looking for the lowest eigenvalue sigma naught squared. Is that clear? Okay. So what we are doing is we would like to use this functional or this variational principle to estimate the lowest eigenfrequency sigma naught or sigma naught squared from this variational principle. So what we know is, well, it's seen here, what we know is that sigma naught squared times 4 pi g times mean density is the absolute minimum of this functional, because it's the lowest eigenvalue and the functional corresponds to the relative minima of this functional. So sigma naught squared is in any case smaller than the minimum of this functional. Now we can put in any function in the functional, and if we get a value for the functional, then the value for some function will be bigger in any case bigger than its absolute minimum. So if we insert in the functional some function, then the value which we get for this function will be bigger than the minimum of this function. Okay, we agree? Putting in or inserting in the functional any function, some crazy function, then it will be bigger than the absolute minimum of that function. That means we could take as a trial function, we could take constant trial function, zeta equal to constant, insert this, then the value of the functional for constant zeta must be bigger than the lowest eigenfrequency sigma naught squared. Okay? Well, this is a particular simple function, because then in the function all the derivatives of zeta are 0. Okay, let's look at the functional again. If we insert a constant function for the trial function, then the zeta by the r will be 0. So this integral will disappear. And here we have constant zeta, so this gives modulus of zeta squared. And we have the same value for zeta star times zeta here. So this is just a number here. And because zeta is constant, we can cancel these the modulus of zeta squared here. So what we are left with is then an expression which only involves the function h and g tilde. And the function itself, the zeta has dropped out of the integrals. So what we are left with then, sigma naught squared is smaller than the value of the functional for any value, but it's smaller than f, for instance, for given zeta equal to constant. So what we are left with is the function h, which is left. This is minus r cubed times the derivative, essentially, of the pressure and involving the gamma adiabatic, divided by the integral over the density times the fourth power of the radius. So we have now an expression for the maximum of sigma naught squared in terms only of quantities of the background model, which is density, pressure, and gamma adiabatic. Well, we are disturbed somewhat by this derivative, so we perform to get rid of this derivative, we perform a partial integration and put the derivative to the r cubed. Then we have a boundary term. The boundary term involves the pressure and the radius. So at the center of the star, the radius term will make the boundary term 0, and at the surface, the pressure will make the boundary term 0. And then we are left with minus, we have to account for another minus. R cubed gives 3 times r squared times, now the derivative is gone, 3 gamma adiabatic minus 4 times p naught, and we integrate over 4 pi dr, and this is corrected for by the integral down there. The factor 4 pi is inserted for convenience. This is 4 pi r squared rho naught times r squared dr. So this is the upper limit for sigma naught squared. Now we rewrite this in a little bit different way. We define a mean of the adiabatic index by an integral, by the following integral. The mean of the adiabatic index is defined as the volumetric mean of the adiabatic index with a weight function. The weight function is the pressure. So if this is kind of a mean taken over the volume and with a weight function p naught. So the mean adiabatic index is given simply by gamma adiabatic times mean times the weight function over the volume divided by the integral of the weight function over the volume. So this is the definition of gamma adiabatic, and if we define it that way, then we obtain that sigma naught squared is given by, that's how we get rid of this gamma adiabatic under the integral. This is 3 times the mean adiabatic index minus 4 times the ratio of the integral over the weight function divided by the integral over rho naught times r squared. So these are well-defined positive functions or positive integrals, and so the sign of the sigma naught squared, which we are interested in, once we are interested in stability or instability, we are interested in the sign whether sigma naught squared is positive or negative. This sign is not determined by these integrals. They are positive. They are determined by the sign of these bracketed term. So whether sigma naught squared is smaller or bigger than 0 is controlled by the mean of the adiabatic index. Mean means it's the volumetric pressure-weighted mean over the entire star. Okay, in this mean, which part will dominate in determining the mean value of gamma? Well, it's the weight function is the pressure. Where the pressure is high, this domain gets the highest weight. So the surface of the star will not get a high contribution or will not contribute to the mean value too much. It's the center of the star which dominates, and this has to be kept in mind. So if gamma is small at the outer part, this does not mean that the mean value is small as well, because the surface terms or the contribution from the outer envelope and the surface of the star is small in general. Okay, stellar dominates due to the pressure weighting. Okay, let's have a look how this adiabatic index looks like. Well, for the two stellar models we have already seen. This is a 60 solar mass star, and this is the 24 solar mass star. Here is the value of 4/3. Well, I haven't said it explicitly, of course. If the mean adiabatic index falls below 4/3, then this bracketed terms becomes negative, and then the upper limit for sigma naught squared is negative. So in that case, we have negative sigma naught squared and we have instability. So if, let me phrase it once again, if the mean adiabatic index is below 4/3, this term becomes negative, and therefore we have to have negative sigma naught squared, and therefore we have to have instability. Is the opposite true as well? If we have instability, then we have to have mean adiabatic index smaller than 4/3. Just from a logical point of view. Is that true? It is not true. And it's many times, it's in the literature, it's confused. Everything. People say, oh, we have instability. It's gamma falls below first. No. Gamma, mean gamma adiabatic falls below 4/3 is sufficient for instability. It is not the opposite. It's not necessary condition. So it's no necessary condition for stability. The opposite, of course. But keep in mind, it's in this sense looking at this inequality, which tells you once I have mean adiabatic index below 4/3, then the upper limit to sigma naught squared is negative, and therefore we have to have instability. But the opposite is not true. It's only that direction. Mean adiabatic index below 4/3 means it is sufficient for instability. And that's the way one has to phrase it, because the opposite is not true. Okay, now let's consider two stars. Well, what we see here, the critical value here, once the mean falls below 4/3, then we have instability. And you see here, in particular in the center of the star, the adiabatic index is always more or less well above the critical value. So if you take the mean over the entire star, because that part gets a much higher weight, the domain where gamma falls below 4/3, even in that case, does not count too much, because the weight function is the pressure, and here we are close to the surface. Weight, the pressure is by orders of magnitude smaller than in the center, and so the region where gamma falls below 4/3 does not count too much, or does not have a big influence. In this case, you see there is also, for the 60 solar mass object, there is also a very small domain close to the surface where gamma falls below 4/3, but elsewhere gamma is is well above 4/3. So the mean adiabatic index is not below 4/3 for any of these cases. By the way, which process pushes gamma below 4/3 here? Could you imagine what might be responsible for gamma falling below 4/3 in these two stellar models? It's close to it's a process which takes place close to the surface. What might push the adiabatic index below 4/3? It must be a process that takes out energy from the system, because the equation of state becomes softer if you plot, for instance, plot the log pressure against log density. Log density, then you usually have such a behavior. And in these cases, if you pass this, then it becomes flatter. This means the gamma goes, the slope of log p against log rho becomes flatter, and then it goes that way. So this is the domain, or this is how it looks once the gamma falls below 4/3. What might be the reason? So the pressure does not increase that fast as before and after this region or this domain density. It's a process which takes out energy from the system, which does some reduces the pressure and reduces the energy density, and pressure behave in a similar way. It's an ionization process. Well, and here it's the ionization for these two stars. It's the high helium ionization which pushes the adiabatic index below 4/3. So that's the helium ionization for the 60, and this is the helium ionization zone, or the position of the helium ionization zone for the 24 solar mass object. Well, on the basis of such diagrams, people even nowadays decide, well, this star has a region where gamma falls below 4/3. So this is unstable with respect to the criterion that gamma, the mean gamma, should fall below 4/3. Once you take this, take the average of the entire star, you will find it's no longer true. And the argument that in the hydrogen, the helium ionization zone, you have a value of gamma below 4/3, and this drives the star unstable. This is simply not true. Okay, so be careful if people tell you on the basis of inspection of the adiabatic index alone that the star is unstable with respect to radial adiabatic perturbations. Okay, so keep in mind the stellar core dominates due to the pressure weighting. Okay, so we have a criterion for instability. Well, if the mean adiabatic index falls below 4/3, we have sigma naught squared smaller than 0, and therefore we have instability. So gamma adiabatic, the mean, of course, smaller than 4/3 is a sufficient condition for instability. And on the other hand, of course, the opposite, that the mean adiabatic index being bigger than 4/3 is a necessary condition for stability, but not a sufficient one. And people confuse sufficient and necessary. Often the terms sufficient and necessary are confused. So be careful once you read papers on that. Okay. Once the mean adiabatic index is above 4/3, you may have stability and instability, and in that case, you actually have to determine the value of sigma naught squared. There is no way to determine stability other than determining precisely the value of sigma naught squared, either by considering the functional or by integrating or looking for solution of the linear differential adiabatic wave equation. Okay, in that case, it's needed to distinguish between stability and instability. You have to perform really you have to solve the eigenvalue problem and determine sigma naught squared precisely. This is the case once you do not meet any of these conditions. Okay. Keep in mind, this is a global criterion. The average has to be taken of the entire star. You cannot just cut the piece you like and determine the adiabatic index in that region and then say, well, I have adiabatic values of the adiabatic index in the region, in the ionization zone below 4/3, my star will be unstable. I have to consider also those parts of the star where gamma adiabatic might be above 4/3, and due to the weight function being the pressure, these might dominate the ionization zone. So the criterion is a global criterion, and the integration have to be taken over the entire star. Central regions have the highest weight, and gamma adiabatic below 4/3 in the stellar envelope does not necessarily lead to an instability. It does not necessarily lead to instability. The fact, the question is, which are the physical effects which can change the critical value for third? Well, there are two effects which may affect this. The critical value is for third. We have not only considered gravity and the pressure. There might be effects which change the critical value from four-third to somewhere else. And two effects which have been discussed in the literature is that rotation may increase. Rotation gives some support to the star, which goes in the direction of increasing, so to say, the pressure, or to give some more support against gravity. That means then the critical value, it's the other way, the critical value which needs to be undergone is smaller if you have an additional support. Relativistic effect may have the opposite effect. Then the star gets more unstable. This means that the critical value of gamma then becomes bigger than 4/3. Another question related to that is is this criterion really important for astrophysical situation? That means, is that criterion relevant for a star, or is that relevant within or in some evolutionary stage of a star? Well, the thermodynamical processes which can push down the adiabatic index below 4/3 is ionization, as we saw it, or it's the disintegration of nuclei, which appears at the final phase of a star. And this third process is the pair creation, the creation of electron-positron pairs from photons. Well, and if we keep that in mind, ionization, disintegration, pair creation, they may be processes which push the gamma adiabatic below 4/3 from a thermodynamical point. The question then is, what is the astrophysical relevance of this criterion, and what are the scenarios in which this criterion is relevant or comes into play? Probably all know it. It's the collapse of a star at the end of its life. Remember, the equation of state for a relativistically degenerate electron gas has an adiabatic exponent of exactly 4/3. So this is the marginally stable state. And in that case, the gamma does not fall below 4/3 somewhere at the surface of the star, but it falls below 4/3 at the center of the star. That's where the highest contribution to the mean of the adiabatic index is found. The pressure as a weight function, it enforces, or it substantially enhances the effect or the contribution from the center. So in that case, we have gamma falling below 4/3 in the center of the star. So it's really important. And well, the scenarios are simply the collapse of the cores of massive stars forming supernovae, or the collapse of white dwarfs once they reach the Chandrasekhar limit and gamma is exactly 4/3. Then only a small kick is necessary to lead to the collapse of the object. So the astrophysical relevance, of course, it's the final fate of stars. It's supernova explosions of type 1 and type 2. So it's really an important effect, and it has to do with the most exciting events in the life of a star. I am supposed to finish now. Well, this afternoon we will have only a few remarks on this instability, and then we will switch to non-radial adiabatic perturbations. Thanks.